At 10:47 on the morning of November 3, 1972, Chief Engineer Harold W. Peterson stood in the control room of the newly completed Dorsey Converter Station, 20 kilometers south of Winnipeg, watching voltage meters climb toward plus or minus 500,000 volts. 56 years old. 32 years with Manitoba Hydro. He was about to energize the longest high-voltage direct current transmission line ever built. A 900-kilometer corridor carrying hydroelectric power from the Nelson River through the boreal wilderness to southern Manitoba. The control panel displayed readings that made conventional engineers nervous. 500,000 volts. Direct current, not alternating. A bipolar configuration that could transmit 1,620 megawatts through two conductors suspended from towers that marched through muskeg, across rivers, and over terrain that had no roads, with no settlements, and winter temperatures that dropped to minus 45. The financial analysts had called it excessive. The provincial government had bet $340 million that Peterson's engineering team could make it work. If the system failed during energization, if insulators shattered, if converter transformers overheated, if the control systems couldn't maintain voltage stability, Manitoba would be left with generating stations in the north and no way to deliver their power to the cities that needed it. Peterson gave the command. Voltage began flowing south from Kettle Generating Station, 900 kilometers away. The converter station hummed, a sound like sustained thunder as mercury arc valves switched DC to AC at 3,000 cycles per second. The meters stabilized. The power flowed. Bipole 1 worked. The problem began in the 1960s, when Manitoba discovered it was sitting on one of North America's largest, untapped hydroelectric resources. And it was in exactly the wrong location. The Nelson River drains 1.1 million square kilometers of watershed, flowing northeast through the boreal forest to Hudson Bay. The river drops 226 meters over its length, creating enormous hydroelectric potential. Sites for massive generating stations existed at Kettle Rapids, Long Spruce, and Limestone. But the river flowed through northern Manitoba, where population density was measured in people per 1,000 square kilometers. The electricity demand was in the south. Winnipeg and the surrounding region, where 800,000 people lived, where industries operated, where the provincial economy functioned. The distance between the two was 900 kilometers of wilderness. Conventional alternating current transmission couldn't bridge that gap efficiently. A C transmission loses approximately 7% of power per 1,000 kilometers due to resistance and reactive losses. A 900-kilometer AC line would lose nearly 6% of generated power to heat before reaching Winnipeg. Unacceptable economics for a massive infrastructure investment. High-voltage direct current offered a solution. Hvdc transmission eliminates reactive losses and reduces resistance losses to approximately 3% per 1,000 kilometers. But in 1966, when Manitoba Hydro began planning, the longest operational HVDC line in the world was 850 kilometers. Nobody had built a 900-kilometer system through subarctic conditions. The engineering community called it ambitious. Manitoba Hydro called it necessary. Harold W. Peterson became chief project engineer in 1968. And he had spent 15 years working on conventional AC transmission before Manitoba Hydro asked him to master a technology that existed in only 3 operational systems worldwide. Peterson spent 1968 visiting the Volgograd to Donbass HVDC line in the Soviet Union, the Pacific DC intertie in the United States, and the Gotland HVDC link in Sweden. He learned that HVDC required specialized converter stations, massive facilities where rotating machinery and electronic valves converted alternating current from the generators to direct current for transmission, then converted it back to AC at the receiving end. The conversion process generated heat, created harmonic distortions, and required precise control systems to maintain voltage stability. Dr. Peterson also learned that nobody had solved the problem of building HVDC infrastructure across terrain like northern Manitoba. The transmission corridor would cross 612 rivers and streams, requiring specialized tower foundations. The route traversed muskeg, waterlogged peat that couldn't support conventional tower bases. Winter construction was impossible. Foundations had to be set during the brief summer months when ground wasn't frozen solid. And the system had to remain operational through winter storms that created ice accumulation on conductors and temperatures that caused metal to contract and conductors to sag. If you want to see how Harold Peterson engineered one of the world's longest HVDC transmission systems through conditions that had never been attempted before, please hit that like button, and it helps us share more forgotten stories like this. And please subscribe if you haven't already. Back to the Nelson River. Construction began in 1970. The first challenge was the Dorsey Converter Station itself, a facility that would house mercury arc valve equipment weighing 1,200 tons, converter transformers rated at 800 megavolt amperes, and cooling systems capable of dissipating 32 megawatts of waste heat. Mercury arc valves were the only technology capable of handling the conversion at the required power levels. Each valve assembly contained a steel tank 4 meters tall, filled with mercury vapor. When voltage was applied, an electrical arc formed between the mercury pool at the bottom and the anode suspended above, allowing current to flow in only one direction. The fundamental requirement for AC to DC conversion. The valves operated at temperatures exceeding 200 degrees Celsius. Cooling systems had to maintain precise temperature ranges. Too cold and the mercury wouldn't vaporize, too hot and the steel tanks would fail. The control systems had to coordinate 12 separate valve assemblies firing in sequence 3,000 times per second. Chief Valve Engineer Robert McKenzie, 42 years old, recruited from General Electric, supervised the installation. The valve halls at Dorsey required foundations 3 meters thick to absorb vibration. The steel frame supporting the valves weighed 340 tons and had to be assembled with tolerances measured in millimeters. McKenzie's team spent 14 months installing and testing the converter equipment. In September 1972, they energized the valves for the first time. One valve assembly failed immediately, an internal arc that vaporized the mercury pool and cracked the steel tank. The failure released mercury vapor into the valve hall, forcing evacuation and a 3-week delay while replacement equipment was installed. Robert McKenzie died in 1989 at age 59. The converter station he built operated for 20 years before being upgraded to solid-state thyristor valves. The transmission line presented different challenges. Tower construction required foundations that could support 45,000 kilogram steel structures in ground that was either solid bedrock or waterlogged muskeg. Chief Construction Supervisor James Thorvaldson, 51 years old, veteran of multiple northern Manitoba projects, developed specialized foundation techniques for each terrain type. In bedrock areas, inner crews drilled holes 6 meters deep and set anchor bolts in concrete. In muskeg, they drove steel piles 12 to 18 meters down to stable soil, then built grillages, horizontal steel frameworks that distributed tower weight across multiple piles. The work proceeded only during summer. Construction crews mobilized in May, worked through September, and demobilized before winter. In 1971, crews erected 1,847 towers across 450 kilometers. In 1972, they completed the remaining 450 kilometers. 3 workers died during construction. One was killed when a tower section being lifted by crane contacted an energized conductor from an adjacent AC line. 2 died when their helicopter crashed during a winter reconnaissance flight. The names: Douglas Mitchell, 38, Carl Bergman, 29, Thomas Kilpatrick, 35. Bipole. I was energized on November 3, 1972, transmitting 1,620 megawatts from Kettle Generating Station to Dorsey. The system operated at plus or minus 463 kilovolts, slightly below the design rating of plus or minus 500 kilovolts. While engineers verified performance, the immediate impact was measurable. Manitoba's installed generating capacity increased by 1,272 megawatts. Electricity rates in Winnipeg dropped 8% as cheap northern hydropower replaced more expensive thermal generation. Industries expanded, population grew. But one transmission line couldn't serve an entire province. If Bipole 1 failed, Manitoba would lose 70% of its electricity supply. Manitoba Hydro began planning Bipole 2 in 1974. The second line would follow a parallel route, adding 1,800 megawatts of capacity and providing redundancy. Construction began in 1977. Bipole 2 was energized in September 1985. By 1992, the 2 bipoles were transmitting over 3,400 megawatts combined, enough to power 2.5 million homes. The system had operated for 2 decades with minimal failures. The engineering community no longer called it ambitious, they called it essential. Today, the Nelson River HVDC system includes 3 bipoles transmitting over 7,000 megawatts from 4 generating stations. Bipole 3 was completed in 2018, following a western route to provide geographic diversity. The combined system delivers approximately 70% of Manitoba's electricity consumption. The Dorsey Converter Station is the largest AC/DC converter facility in the Western Hemisphere. The original mercury arc valves have been replaced with solid-state thyristor technology, devices that perform the same conversion function using silicon semiconductors instead of mercury vapor. When the upgrade increased efficiency and reduced maintenance requirements, but the fundamental vulnerability remains. Manitoba's economy depends on 3 transmission corridors functioning normally. A simultaneous failure of the bipoles, whether from a geomagnetic storm disrupting converter operations, a coordinated physical attack on transmission towers, or ice storms bringing down conductors, would immediately require emergency power imports from Saskatchewan and the United States. Manitoba Hydro maintains interconnections with neighboring systems, but the import capacity is approximately 1,000 megawatts. Losing 7,000 megawatts of northern supply would exceed import capacity by a factor of 7. Our grid operators would have minutes to implement emergency load shedding, deliberately cutting power to industrial customers and rotating blackouts through residential areas. Aluminum smelters, nickel refineries, and manufacturing plants would shut down. Hospitals would switch to emergency generators. Water treatment facilities would operate on backup power. The economic impact would exceed $800 million per week. In March 1989, a geomagnetic storm caused by solar activity induced ground currents that disrupted converter operations, forcing both bipoles offline for 9 hours. The blackout affected 1.4 million people. Manitoba Hydro has since installed protective systems to guard against geomagnetic events, but the vulnerability remains. Unlike generating stations that can be restarted independently, the HVDC system requires both ends operational simultaneously. If converter equipment at Dorsey failed catastrophically, Northern generating stations would have no way to deliver power south until repairs were completed. The system has no redundancy beyond the 3 bipoles. It operates continuously, transmitting enough power every second to light a city, trusting that towers remain standing, insulators remain intact, and converter equipment continues functioning. Harold W. Peterson retired from Manitoba Hydro in 1981 after overseeing the completion of Bipole 1 and the early planning for Bipole 2. He died in 1998 at age 82. The engineering principles he established, bipolar configuration, plus or minus 500 kilovolts operation, redundant converter equipment, remain the foundation of Manitoba's transmission system. James Thorvaldsen continued working on northern construction projects until his retirement in 1988. He died in 2007, age 88. The foundation techniques he developed for muskeg terrain have been used on subsequent transmission projects across northern Canada. The Dorsey Converter Station operates 24 hours per day, 365 days per year. Control room operators monitor voltage, current, and harmonic distortion across all 3 bipoles. Transformers hum at 60 Hz. Thyristor valves switch DC to AC thousands of times per second. Cooling systems dissipate waste heat into the Manitoba air. And 900 kilometers north, water from the Nelson River spins turbines at Kettle, Spruce, and Limestone generating stations. The power flows south through conductors suspended on towers that march through wilderness unchanged since Peterson watched the first voltage climb toward 500,000 volts in November 1972. The system continues. Manitoba depends on it continuing. If this story moved you the way it moved us, do me a favor, hit that like button. Every single like tells YouTube to show this story to more people. Hit subscribe and turn on notifications. We're rescuing forgotten stories from dusty archives every single day. Stories about infrastructure systems that power modern life. Real people, real engineering, real stakes. Drop a comment right now and tell us where you're watching from. Are you watching from the United States, United Kingdom, Canada, Australia? Our community stretches across the entire world. Or you're not just a viewer, you're part of keeping these memories alive. Tell us your location. Tell us if you've worked in electrical engineering or power systems. Just let us know you're here. Thank you for watching, and thank you for making sure Harold W. Peterson, Robert McKenzie, and the 3 workers who died building this system don't disappear into silence.